not necessarily the hard part, right? If you're given a formula, I assume at this point, like there's two things that you have to be able to do. You have to be able to take a formula that involves a couple of variables over here and write a related rates formula. And so it makes a difference whether something's a constant or not.
On the exam, are we going to get like these formulas to begin with?
If I don't like it to be memorizing, so please don't go home and say, oh, I got to memorize all this stuff I learned in grade 8. If it's a difficult formula, or if I want you to do this, I might say, given that the volume of a cone is this. Okay? But I also may give you something where you have to... Yeah. Often they will, they don't care that you...
The hard, like, cones and stuff are probably IR squared.
You need to think about whether something's a constant or not. You can, if you don't realize that when something's a constant, it's a lot easier to work with, you'll still get sort of a right answer. You can work with it, but it's a lot easier to realize something's a constant. It says if h is a constant here, if that's a constant, when you're writing this formula, dv dt, if you differentiate both sides with respect to t, if you do the derivative of everything on the other side here, of 1/3 pi r squared h, if this is a constant, you can put it outside, right? All of this stuff you can put outside. That can go outside of the, you don't have to worry about the constant. And this can go outside as well, right? If it's a constant, you don't have to worry about it. You don't have to do the product rule. You can just go straight to 1/3 pi h and then the derivative of r squared, which is, of course, so you got your 1/3 pi h, and then you have 2r times dr dt. That's what the rate of change of volume is. So this is something, rate of change of volume, you have to think of, water being poured into or out of something, sand filling up something that you're doing to do with volume. There's a question later, or earlier actually, it's a cone-shaped reservoir or something. You have some cone-shaped reservoir and stuff's either pouring into it or pouring out of it. The volume is, it's water or something and it's going down. This is a sphere. Okay, a sphere getting larger, blowing up a balloon if you're imagining it's a sphere. This is the volume of a box where you're looking at three things. It's going to have lots of variables involved because you're going to have each of those variables. Each of those is a variable, right? Each of them is a rate of change of a different thing. Plus, you're also going to have the length, width, and height involved. I'm assuming that you can pretty easily come up with this. This you can come up with the rate of change formula. You start with something involving the variables themselves, and then you generate the related rates formula. If you're not given a formula, you need to write one based on a proportion or some other thing, Pythagoras, something or other. So you're either given the formula or you generate your own. For this one, I know that a lot of you said, well, if I differentiate this, it's sec squared theta times d theta dt, right? On one side. And on the other side, you have y over 100, like the derivative of that. You don't need to look at this as the quotient rule right off the bat. If something's a constant on the bottom, just make it 1/100th outside times dy dt. A lot of you, I noticed, were doing this as the quotient rule here. You were using the quotient rule, which works, but you get something a lot more complicated. It's easier to look at that as a constant and put it outside first. And then some of you were isolating this and putting the secant squared like this, 1 over secant squared on the bottom over here. You can make that cosine squared because that's what you do on your calculator anyways, right? So you could make it, if we can write it up here, you could make it d theta dt equals cos squared on the top divided by 100 times dy dt. This has to do with, well, there's a question later on that has to do with a balloon. You're standing here Actually, I guess your face is right against the ground because it doesn't start higher up, but you can imagine. You're looking at a balloon. Let's try something here.
Hole.
This could go terribly wrong, but we'll see.
Camera on the ground.
You have you're in a hole. You're in a hole, and there's a balloon here. Here's the balloon, and
Looking at it.
well, I need the lines to be all connected here because I want to do this. So the balloon is. This is not going to work actually.
You should just put a camera on the ground.
Here's the angle. Okay, let's just move the ground up here. Here's the ground. He's in a hole. Okay, here's the ground. He's in a hole, standing in a hole. There's the ground. Okay. Now the problem is this might not work, but this is must not expand the guy's head. So the balloon is going up in the air, right, like that. Now ignore the fact that the black line on the bottom's going up as well. Okay, you're ignoring that?
Yes, I am.
You're okay ignoring that? I don't actually like that. I think we can do better at this.
It's okay.
This formula in this situation, if the balloon's going up, it relates the angle that you're looking at the thing to the height. So you're thinking, how fast is this height changing compared to how fast this angle is changing? You could think about just intuitively, does it make sense that, let's make this shorter first of all here, if it was there, does doubling the height double the angle every time? It doesn't really, right? Because trig functions don't work in that linear fashion. So doubling the height doesn't double the angle. Once you're up here, it hardly changes the angle at all. It changes the angle quite a bit down here. Okay? But then up here, doubling it doesn't really change the angle that much. That's why it's not just directly this is this times some constant, right? That's why this is involved here. If it was that when one was doubled, the other was doubled, this wouldn't be here, right? It would just have maybe this thing in the bottom. This wouldn't be here. If it said the rate of change of the angle is 1/100th of the rate of change of this, it would just be, that would be a direct relationship where one's doubled, the other's doubled, but it's not, right? The fact that that's involved means that accounts for the fact that it doesn't just change like that. You're looking at rates of change and how they're related. One I wanted to show you or some of the ones I wanted to show you were these ones. Some of you have tried these already. Perhaps we can stop this and start again and we'll run out of time here.